Alright, if you missed school on March 4th or 5th, or if you just want to review what we talked about those days, I'm going to put together this video. I'm putting together this video for that specific purpose. First thing we talked about on Monday was intermolecular forces. We talked about hydrogen bonding, and this gives you the definition of those. This is a picture we really didn't talk about, but it is all about poles. Three types are dipole forces, hydrogen bonding, and London dispersion forces. Dipole forces, the force of attraction between the positive end of one molecule and the negative end of another. This force is the strongest of the three. And a good example is hydrochloric acid, shown over here in the bottom right. One end, the chlorine end, is negative, the other end is positive, so when you have a glass filled with hydrochloric acid, or a beaker filled with hydrochloric acid, the positive ends of the hydrogens will be attracted to the negative ends of the chlorines on other molecules. So it's an intermolecular force. This is a picture we didn't really talk about. Hydrogen bonding. When a hydrogen is bonding to a very electronegative atom, the compound becomes really polar. And what happens is that, same thing with dipole forces, except to a greater extent. So it's debatable as whether hydrogen bonding is more powerful than dipole forces, or if dipole forces are more powerful than hydrogen bonding. Different sources say different things. We will go by the book. The book says that dipole forces are stronger in general. Hydrogen bonding comes in second, and then the last one is London forces, which I'll talk about in a second. So this is really just how, when you have a really electronegative atom attached to hydrogen, that causes a really strong polar force. So that causes even greater poles to be made. So that positive is really positive, and the negative is really negative, and they'll create this weird attraction. Last one is London forces, or London dispersion forces. This is a totally temporary attractive force. It's very small. It is the weakest force out of these three. And this is the only one that can work in nonpolar compounds. This is the only one that can work in nonpolar compounds. The other two only work in polar compounds. This one is only in nonpolar. Or this one can technically work in both polar and nonpolar compounds, but again, this is the only one that can work in nonpolar compounds. The last thing we talked about was polyatomic ions. And this is just a charged group of covalently bonded atoms. We'll go in a moment. I'll go into how to construct the structure here, which is called ammonium, and it's basically NH4 with a positive. And this positive shows that it has a positive charge, overall positive charge. And this explains a little bit about polyatomic ions. So let me go into how you construct these structures. And the first one we'll talk about is, like I just showed you, NH4 and plus, NH4 plus. Whenever you have a plus sign, that's telling you it's a plus or minus. It tells you this is a polyatomic ion. So whenever you see a charge sign here, whether it's positive or negative, that tells you it is a polyatomic ion. And real quick, we're just going to break down the word. So polyatomic ion. At this point, we know what an ion is. And normally when we talk about ions, we're talking about atoms, something with a positive or negative charge based on the electrons that it has lost or gained. Well, poly just means more than one. Atomic just means related to atoms. So this is a group of atoms, more than one atom. And so it's a group of atoms that are ions. And that just means they have charges. So it's exactly what this chemical formula is showing. So now let's go through the basic steps to construct this guy. So step one, electron dot structure. So N has 5, each H has 1, and there's 4 of them. So that gives you a total of 9 electrons. This positive tells you that this whole thing, this whole group, has overall positive charge, meaning that it lost 1 electron compared to what it would normally have. So that means that normally we would have 9, whereas this guy has 8. So the structure you're actually going to create only has 8 electrons in it. And that's 8 valence electrons. The total electrons is a little different. But we're considering 8 valence electrons. So now which one goes in the middle? The least electronegative one goes in the middle. And in this case, we'll just stick with the fact that hydrogen never goes in the middle. So you'll put your nitrogen in the middle, because hydrogen never goes in the middle. Just create your single bonds, and you got 4 of them, because you got 4 other atoms. So 1, 2, 3, 4. You got 2, 4, 6, 8. So that is your structure. Keep in mind that you can't add any more electrons here anyway. Like, that's as good as it gets. You can't add electrons here. You can't do that. Or here. That's not allowed. So that's your structure right there. That's it. The one thing you would do to denote that this is a structure that's polyatomic is that you would have big brackets here. And you put that plus sign that you see over here. That shows this is a polyatomic ion. The other structure we did, PO4 3 minus. PO4 3 minus. So same thing. Draw your dot structures, add all up the dots, and follow this what this negative sign is telling you, or this negative 3 is telling you. So P 1, 2, 3, 4, 5. Each oxygen is 1, 2, 3, 4, 5, 6. And that's times 4. So 4 times 6 plus 5. Well, 4 times 6 is 24 plus 5. That's 29. So normally this structure would have 29 electrons. Since we have this minus 3 here, it's a polyatomic ion. This tells you you have 3 additional electrons because you have 3 extra negative charges. 3 extra negative charges. 1, 2, 3 extra electrons there. So you have to add more electrons. That gives you a total of 32 that your final structure should have. So whatever we put together should have 32 electrons in it. Which one goes in the middle? The least electronegative one goes in the middle. In this case, phosphorus is definitely less electronegative. It's more to the left on the periodic table. Create your single bonds. Again, keep it simple. Now keep in mind, oxygen is not an exception to the octet rule. Oxygen wants its 8. Phosphorus wants its 8. Oxygen wants its 8. Everyone wants 8 here. There's no exception to the octet rule. And notice phosphorus is already happy. Phosphorus is already good to go. So we just got to add electrons to please all these oxygens. So start adding your electrons to follow the octet rule. 8, 8, 8, and 8. So 8 plus 8 is 16, plus 8 and 8 is 32. This is a structure with 32 total electrons. You want to show it's a polyatomic ion by drawing this bracket with this 3 minus here. And that is the structure of PO4 3 minus. This is what we talked about on March 4th and 5th. And this is what we went over on March 5th in case you missed those days and if you need to review those topics. I hope this was helpful.